Welcome back to video lecture series on sensors and actuators. In the previous module 1, we have seen the introduction to sensors and its characteristics. So how to define a sensor, what are the applications of sensor, and what is a transmitter, and how to define a transducer, and what are the different classifications of sensors. The classifications of sensors we didn't see in detail. Just you have seen what are the different types of classifications of sensors. And then what are the characteristics, how to select a sensor, what are the parameters that is used to select a sensor, and what are its characteristics. So in module 2 we have classified the sensors into two categories. One is the classification of sensor 1. So in this module 2 we are going to see the electromechanical and the mechanical sensors and its types, and what are the classification of these two methods, and explain the working principle of each methods. These are the topics I'm going to cover in this module 2. One is the mechanical and electromechanical sensor, and what are the principles and what are its classifications, and in that what are the different methods for each classification. So one is the resistive sensor, in that there are different methods, as well as inductive sensors, and then capacitive sensors, and then ultrasonic sensors. So all these sensors we are going to classified as a classification sensor 1 in module 2. So first let me start with the mechanical sensors. So in the previous module you have seen sensor. So sensor is nothing but something that detects some changes in the physical parameters. So in the physical parameters will detect some changes, so that we call it a sensor. So now we are going to see what is the mechanical sensor. So mechanical sensor, here also it will detect some changes. What changes it will detect? It will detect some physical properties, such as it may be a force, or it may be a pressure, or it may be a displacement or position. So if it detects these type of physical properties, then it comes under the category of mechanical sensors. So these sensors are widely used in the manufacturing in a day-to-day life, and also whatever the devices to monitor and control in industry applications, these mechanical sensors will be widely used. So hence I can define a mechanical sensor. It detects some physical changes such as displacement, force, or pressure, and provides some mechanical output. What mechanical output it can produce is, it may be a displacement, or it may be a deformation, mechanical deformation. So the sensors will directly measure the physical changes and converting them into an electrical signal. So it will directly measures the physical changes, and it will not convert into an electrical signal. So in mechanical sensor, only detect the thing. It will not convert into an electrical signal. So next comes the electromechanical. So electromechanical, the name itself, we can understand that it has both electrical as well as the mechanical. So it is a combination of both electrical and mechanical components to detect some physical changes. What such as it may be a pressure or temperature or position or force, and converted into some electrical signal. So that we call it as electromechanical sensor. So the sensors use the mechanical movement because it is an electromechanical, right? So mechanical movements or deformation or a displacement. Based on this, it will produce some output into an electrical output. So that electrical output only we are going to measure and for used for analysis. So I can define an electromechanical sensor that detects the mechanical changes. So let it be a force, displacement, or pressure, and converts them into an electrical signal. It may be a voltage signal or current signal or resistance, whatever it may be. And these sensors use both electrical and mechanical components to provide an electrical output. Whereas the mechanical sensor, it will sense only the mechanical property, and it will not convert into electrical signal. Whereas this electromechanical, it will take the mechanical properties and convert into an electrical signal like voltage or current or resistance. So while performing these two mechanical and the electromechanical sensors, two things we need to concentrate on. One is sensing, another one is transduction. Already we have seen both in previous module. Sensing is nothing but it is used to sense. What it will sense, whatever it is detecting, that gets sensed from the physical environment. Whereas if we take a mechanical, for example, if we take a mechanical sensors, so the mechanical sensor, it may have some, it has a strain maybe there, or compression we have, or it may have some motion. This is for mechanical sensors. If you take electromechanical sensors, uh, it will be always produce some changes in the resistance or capacitance or inductance. So it will, when I say principle of sensing means, it refers to the sensor detects changes in the physical environment. Only the sensing part. So that is sensing, principle of sensing. Coming to transduction, so it will discuss some methodology for energy conversion or any signal conversion. So this transduction, it involves converting whatever it gets sensed from the mechanical input into some useful output. Useful output in the sense we need only the electrical signal. So it will convert the mechanical input, the displacement, force, compression, anything into and some electrical signal. So that we call it as transduction. It's nothing but the transducer. What's the role of transducer? Transducer does only this transduction only. Whatever the sensor output we get, that will be converted into some electrical signal. So here when you say resistive transduction means the change in resistance that is happens due to strain. Strain is get from the mechanical, and capacitive transduction means due to displacement there is a change in the capacitance. Inductive transduction means due to motion there will be a change in the inductance. So like that, which due to which mechanical property or any property which is converted into some useful output, then I can say that is a transduction. Let's move on to the classification of electromechanical sensor. So these are the different types of electromechanical sensor. One is a resistive sensor, capacitive sensor, inductive sensors, and piezoelectric sensors. First, let's move on to the resistive sensors. So resistive sensors devise nothing but it will measure the changes in the resistance. Change in resistance we are going to measure. How we get the change in the resistance? That is caused by mechanical things like strain or displacement. Due to displacement there will be change in the resistance. Due to temperature there will be change in the resistance, or due to force there will be change in the resistance. So change in resistance will happen with these physical phenomena like strain, displacement, temperature, or forces. So based on these category, this is classified as two. One is the strain gauge, another one is the potentiometers. When I say resistive sensor means change in resistance you are going to measure. When I say inductance means change in inductance we are going to measure. So this is the strain gauge construction. This is the construction of the strain gauge. So here you can see this is a carrier. So inside the carrier you have a strip. The strip is placed. It is in grid pattern. Okay, so this grid pattern has a metallic wire that is placed inside, and these two are connected with, this gets soldered, and two leads are taken from this. So here the thing is, this metallic wire, whenever I say strain, is nothing but deformation. Deformation means some changes will take place. What changes it will take? Whenever I say strain, it may be two types. Two types of strain we can have. One is the positive strain and the negative strain. Positive means tensile strain, or the negative means compression strain. For example, I'm having a spring. Okay, uh, when I come when I compress this, what will happen? It gets compressed. When I release that, it gets expanded. This compression we call it as negative strain, and this expansion, this stretched, right? So that we call it as positive strain, that is tensile strain. So when I add some weight on a strain gauge, what will happen? It gets compressed. When I add more and more of weight, it gets compressed. So when I say compressed, it is nothing but the negative strain. When I remove the weight one by one, automatically it gets expanded. Okay, so that we call it as tensile strain, tensile strain. So this is happens in this. So due to that, what will happen? This experience, this strain will be directly proportional to the strain gauge. So this is what the formula, epsilon is equal to del L by L. This is rate change in the length divided by the original length, that gives the strain. So already this is the original length. Due to the applying some force or something, what will happen? It gets compressed. So automatically there is a change in the length. So that we call it as strain. That you have to find. That is the epsilon. So this will be used for the next case, that is strain gauge working. So that strain gauge is placed in the, this is nothing but your Wheatstone bridge. Okay, so now here I'm adding some weight. Due to that weight, what will happen? This strain gets compressed. Okay, so here I have taken, this is the Wheatstone bridge. So opposite ends are equal. Okay, so when I say this R1 and R3 is equal to R2 and R4, but R4 is connected to some strain gauge. So now at null position, if you're not doing anything, at null position what will happen? R1 and R3 are equal. R1 R3 is equal to R2 and R4. Now, when I adding some weight, what will happen? The strain changes. It produces some compressive strain. So due to that, the length changes. Due to that, the epsilon gate changes. Okay. So this changes. What will happen? Makes the Wheatstone bridge unbalanced. So initially it is balanced. When it is balanced, the voltage is zero. When it is unbalanced, what will happen? There will be change in the resistance due to the addition of some weights, due to the addition of some strain in the strain gauge. The resistance get changes. That change in resistance, how much amount of resistance get changes, that will be directly proportional to the amount of strain. So in this way only we will calculate the change in resistance is calculated, and that will be calibrated to the strain, how much amount of strain we have applied. So that is what the formula here, del R equal to R into G into epsilon, or R is the resistance and G is the gauge factor. That depends on what material you are using. Based on the G will change, and E is the epsilon, which is nothing but the strain. So from this we can easily find the change in the resistance. So the change in resistance is always proportional to the how much amount of strain we have applied. So these are some of the steps for the strain gauge. First you have to apply the load. After, when you apply the load, what will happen? Deformation of the strain will take place. Whenever the deformation takes place, that means that there is a change in the resistance. The change in resistance we have to convert, that is proportional to the change amount of strain. So next comes the potentiometer type. So before that, we should know what is the sliding contact devices. So sliding contact devices is nothing but resistor transducer. So here we have seen a resistor, right? One resistor. But here it is, a wire is wound over series of resistance. Okay. So we have a slider on the top. So slide one end is, this end is fixed, another end is mobile. So from this distance is L. Okay. So resistance is rho L by A. A is the area of this one, and L is the length. So when at this position, when you adjust this, what will happen? The length will get changes. When the length changes, automatically the resistance will changes. So in this way also we can find the change in the resistance. So this is the sliding control. So this is widely used for the voltage divider. Wherever you want the voltage divider, then we can have this potentiometer. So here this is the slider, and this resistance is R1, this is R2, this is the voltage here. When you're adjusting the slider, what happens? The voltage will get divided from this resistance to this resistance. That's why it's called as the voltage divider. So here there are two types of potentiometer. One is potentiometer is also called as a, we can call it as a pot. It is nothing but the variable resistor. It has three terminal like this, three terminal. So two terminals are fixed already. One is fixed and another one is a mobile one. It's a variable one. Okay. And so here we can measure the output voltage. So now the slider is here. So now when I'm adjusting the slider up to this position, this distance, this how much amount of voltage that is obtained by using this slider. So that can be identified, that can be calculated, measured from this potentiometer. So the slider is adjusted manually over this is the resistive strip to change in the resistance value from 0 to the higher value. Okay, so when the resistance changes, automatically the current in the circuit is also changes. From that we can easily calculate the resistance value. Next is the types of potentiometer. There are two types of potentiometer. One is the rotary potentiometer, another one is the linear potentiometer. So rotary potentiometer, it measures the angular displacement, whereas the linear potentiometer, it measures the linear displacement. So this angular rotary potentiometer is used in the radio. The radio we are adjusting the what is that station. So 91.1, 92.3. So when adjusting that, we're just fixing to the slowly we'll adjust. At one point we will get the audio very clear. So that we'll adjusting that. So that is the that displacement will measure. So that is the rotary displacement. And linear displacement is used in the robotic arm positions. So by taking the arms, it will move this more linearly. It will move and it will come to its origin position. So that cases we can have this linear potentiometer. So some of the example radios and all the musical instruments and this robotic and wheel angle measurements, this rotary is used. So next comes the inductive sensor. So resistor sensor means it will measure the change in the resistance. Inductive means it will measure the change in the inductance. So inductive sensor is a type of proximity sensor. So proximity, when we're talking about the proximity sensor, it will detect the metallic objects without any physical contact. So this inductance always is based on the principle of electromagnetic induction, and it's widely used in the automation and robotics and security applications. So when coming to the working principle, the inductive sensors, it will generate some alternative magnetic field. So you have an inductor coil. So when our inductor coil is placed, automatically it will produce some alternating magnetic field. So whenever a metallic object is present in that, what will happen in the particular field? In a particular field, if it is a metal is present, so this will detect this and find the find the eddy current. It induces some eddy current, so which will affect the coil impedance. So this change is detected by the sensor circuit and it produces some output signal. So this is what is the principles. Whenever a metallic object is detected, what will happen? The sensor circuit, it produces some electrical, that is output signal will be triggered, generated. So these are the components of the inductive sensor. One is oscillator for generating the AC magnetic field, and for coil that produces the electromagnetic field, and you have a detector circuit which is used to sense the impedance, how much amount of changes takes place in that, and then output circuit, whatever the changes have sensed, that will be converted into an electrical signal. So in this first one is mutual inductance change type. So mutual inductance change type sensor, it is based on the principle of mutual inductance. So that means where the mutual inductance between the two coils varies due to the movement of the target object. Typically, it may be a ferromagnetic or a conductive material. So you have considered this is coil 1, this is coil 2. So in this coil 1 is connected to this power supply, and so when you are bringing this coil 2 closer to this, what will happen? It produces a change in the magnetic field in the first coil, it will induce some EMF, that is electromotive force in the second coil. So this we call it as mutual inductance. So when a wire, this is the wire wound with some coil, okay, and another, this is the secondary coil 2. This is bringing closer to the coil 1. So due to that, what will happen? There is a change in the magnetic field in the first coil will be induced in the coil 2. So this property we call it as mutual inductance, which is equal to M equal to K into root of L1 L2. This L1 is the self inductance of the coil 1 and self inductance of the secondary coil, and K is the coupling coefficients. So that is the mutual induction type. And next one is the reluctance change type inductive sensor. Reluctance is nothing but opposition of the magnetic field. So whenever a magnetic field, how much amount it gets opposed. So that is called as reluctance. So these sensors is based on the principle of the inductance of the coil that depends on the reluctance. So the reluctance of the magnetic circuit. So when a ferromagnetic object changes the path of the magnetic flux, the reluctance of the magnetic circuit varies, leading to change in the inductance. So whenever the reluctance changes, that will lead to the change in the inductance. So this is the property of the reluctance change type in inductive sensor. So this is the reluctive type. So this is the core. We have a core. So this is the sensor. It consists of a coil. This is the coil. This coil is wound on this core. This is the core. Now, when an external ferromagnetic object, suppose here you have the ferromagnetic object that is moved closer to the coil or away from the coil, what will happen? The magnetic reluctance, the reluctance of the magnetic circuit changes. It comes to closer or when it comes away from this. So the reluctance will change. So that change in the reluctance, that will change the inductance. So in resistance, so due to the change in the resistance will changes the strain. Similarly here, the change in the inductance will be detected and that will be converted into electrical signal. So this is the working principle of a reluctance type. So this will be used for the automatic applications to measure the rotation speed of the gears. So M is the magnetomotive force, which is equal to flux into reluctance, that is phi into R, and phi is equal number of turns in I divided by R. R is the reluctance. So how much amount of flux linkage which is given by psi equal to N into phi. So from this you can find L equal to psi divided by I, which is equal to N square by R. So in this way we can find the how much amount of inductance. The change in inductance will be calibrated to the into an electrical signal. So next comes the transform action type. So here you have a two coil. One is the primary circuit. This is the secondary circuit. Okay, so if a metallic object such as a piece of wire is placed within the magnetic field, piece of wire, this is the magnetic field. If it is placed inside this, what will happen? This produces some electric current in the secondary conductor. If only one coil is wound on the iron core and in the secondary coil you have a bulb, so this due to magnetic induction, what will happen? The secondary coil, due to the oscillating of the magnetic field, this produces some electric current and makes this bulb to glow. So this we call it as electromagnetic induction. So this principle is used in all the transformers. So one of the application is LVDT, that is linear variable differential transformer. So for that application, this transform action type is used. This is due to the electromagnetic induction. So that electromagnetic induction is used in this linear variable differential transformer. We call it as LVDT. It is one of the famous very important applications of the inductor transducer. That is used to measure the displacement. It can also used to measure the pressure and force. So it's based on the principle of mutual inductance, what you have seen in the previous slides. So LVDT. So this is the construction. So here you have two coils. One is the primary coil, another is the secondary coil. So the primary coil, you have coil is placed, and secondary coil is split into two, secondary coil 1 and secondary coil 2, and this is connected in such a way that it is not connected, it is connected in series opposition. When I say series connection means continuously it is connected. So if it is in series means you will add those voltages in each coil, how much amount of voltage developed and how much amount of EMF developed. Based on that we will add. But series opposition means it is not an addition, it should be subtracted. There is a difference in the voltages. So this is, let me take this secondary coil 1 voltage is V1, secondary coil 2 voltage is V2. Then again the output voltage is V1 minus V2. Because it is not connected in series, it is connected in series opposition. That means this end is, if it is series connection, this end is connected to this. But this end is connected to the another end, and this is connected to the output voltage. So this we call it as series opposition. So S1 and S2 have an equal number of turns and are set up in series. It has equal number of turns for both S1 as well as S2. So now based on the core movement, how the output is generated. That is what we are going to see in this LVDT. So here we are considering three cases. This is the case 1 where the core, this is the core, is iron core, this is placed at the center. Center in the sense it will fully covered with both the coils. So what will happen when a core is placed between these two, a magnetic induction will take place, and this will produces an voltage of Vs1, and here it produces the voltage of Vs2 or as V1 or V2. This voltage is V1, this voltage is V2. But this output voltage is V1 minus V2. But here both are same values because it has equal number of turns. The voltage EMF generated will be same, voltage will be same, and the voltage here also same. So when it is positioned at the center, this will be equal to Vs1 minus Vs2. Both are equal. Therefore, the output voltage is 0. So in this case, I can say that there is no displacement. There is no movement. Simply we are just placed one core there. That's it. Coming to the second case, so now the core is placed like this, where it has more of mutual inductance with the secondary coil 1, but not more with the secondary coil 2. So that means the voltage developed in the S1 is higher than this. This is less. So when you are talking about the voltage V0, V1 minus V2. So whenever V1 minus V2 means V1 will be higher than V2, therefore you will get a positive voltage. That's why it is given as V1 is greater than V2. That means the voltage in the V1 is higher. Coming to the third case, now the coil is placed like this, where you have more induction with the secondary coil 2, but less with the secondary coil 1. That means V1 is less than the V2. V2 will be higher. Therefore, the output voltage is V1 minus V2, which is higher. V2 is higher. Therefore, you will get a negative voltage. That means this is V2 is greater than V1. So, you will get a negative voltage. So, in this way, we can find the core movement. So, based on that, we have drawn the diagram. Since that this is the null position at center, one will be higher, another one will be in negative side. We have all negative values, and this will be all positive voltages. So this is the input output curve of the LVDT. So this can be used in the industrial automation, for monitoring the aircraft control services surfaces, in prosthetic devices, in biomedical applications, and then measuring the bridge deflections, and then in robotics arms it will be widely used, and for throttle position sensing for an automotive industry this LVDT is widely used. So next one is the proximity sensor. So proximity, when I say talking about the proximity sensor, it will detect the presence or the absence of the object in a specific region, specific area, without any physical contact is not needed. Okay, so that is we call it as the proximity sensor. So when a disturbance is detected, the sensor triggers an output signal, typically in the form of electrical signal indicating the detection. So you can also have a automatic door opening. So automatic door opening, how this will work is when this is the door, this is the door. A person is moving from this. So when a person comes here, the door is not open. When it comes this portion, the door is not open. When it comes to this portion, door is not open. When it comes to this portion, the door is open. That means this is one. This is the target, and this is person. This is the sensing part, and this is the target. So as the target is reaching this, so they will fix the threshold range. So this distance is some one some 20 centimeters or 10 centimeter. Then the door will open. Some threshold is maintained there. So this act like a capacitance. This is one plate, this is another plate. So capacitance is epsilon A by D. When the distance changes, automatically the capacitance changes. As the distance changes, so here also distance changes, but it doesn't detect. When it comes to this portion, it doesn't detect. When it comes to this portion, it gets detected because this threshold value is matched with that. Automatically the sensor will open. Sensor will make the door to Sensor will sense and gives the signal to the actuator, so that actuator makes the linear actuators to open the door. That is what is happening in the automatic door opening. So in that we are going to see what is the capacitive proximity sensing working. So that is what is I explained now. The first one is sensor generates an electrostatic field between the sensor plate and the target. So one is the sensor plate, and another one is the target plate. Target is what we are going. So when the target object approaching the sensor, just as assuming this is the sensor and this is the target. Okay. So when the target is approaching the sensor, the distance in the plate changes. Even if the distance in the plate changes, it will not sense. When it will senses, this distance alter the, it will change the capacitance value, because C is equal to epsilon A by D. D changes, automatic capacitance will changes. So what will happen? This capacity, there you have an RC, here you have an RC oscillator. So the capacitance changes, automatically the oscillator begin to oscillate. Okay, and then this will keep on oscillating. When this oscillation will get stopped means when it sends some threshold level. We have to fix some distance. When it reaches this distance means automatically the actuator will make to open the door. Door will get open. So that will be given with the help of the, once the sensor activates, then the oscillation means reaches the threshold level. When it reaches the threshold level, the sensor get activated and make the activated and gives a signal to the actuator to open the door. This is what happening in the automatic door opening. So this inductive proximity sensor is it is also used only for the detecting the metals, whereas the capacitor sensor is used to detect plastic targets. You have a plastic target, you have a metal target. In what is that Coke Coke industry, there you have a bottle filling system. There you have proximity sensor because it is a metal plate, metal can. Okay, metal can. So when continuously the bottle will move, can will move. Once when the can, whenever the can is present, the proximity sensor will sense the can What will happen? The next step is it will immediately it will stop, and then the coke will fall into the coke will fill the can. Once it gets filled the can, next one is the stepper motor will run, and the next bottle will come. So this will happen continuously. So it will detect whenever if there is no bottle for the second case, it will not stop. It will move to the next. When it detects the metal, then only it will stop. So this is some of the applications for object detection and for liquid level detection in touch sensors, smartphones, and others. We have this proximity sensors. This is for the capacitive. In inductive proximity sensors, detecting the metal parts, a conveyor belt for sorting the quality control, and car parking for automatic vehicle detection. In all the toll booths, we have this inductive proximity sensor. So next comes the capacitive sensors. So here also, based on the change in the capacitance, it will measure only the change in the capacitance. So already I said C is equal to epsilon A by D. This epsilon R and epsilon naught is the relative permittivity of a dielectric medium, and epsilon naught is the permittivity of the free space, and A is the area, and D is the distance. So this is the, so in the capacitance I can say that two plates, this is the bottom plate and this is the top plate, this is the bottom plate. In between you have the dielectric medium. Okay, so in the dielectric medium, so as the plate, as the distance changes, you will have the capacitance will change. If the area changes, also the capacitance changes. Two categories we can have. By changing the distance, capacitance changes. By changing the area, the capacitance will change. So first let us see what is the change in the area of the plates area. So this is one metal, this is the another metal. Okay, so this diameter is d1 and this diameter is d2. This is area, right? So whenever you're talking about area, this is a circle. Therefore, the area of the circle is pi r square. So in the place of A, you have to use this pi r square divided by 2. Area of the circle is pi r square by 2 into D. So this is, suppose if it is a semicircle, then you have to put 2D. Area of the circle is pi r square. If it is a semicircle, pi r square by 2. So then Cmax is equal to epsilon A by D, and epsilon is there, A is the pi r square by 2 into D. That is what is shown here. One is the fixed plate, another one is the mobile plate. This is the fixed plate is like this, and mobile plate will go inside and come. Okay. So this is where the area of the plates get changes. And next, the change in the distance. If the distance gets changes, automatically the capacitor will change. This is one fixed plate. This is the mobile plate. The mobile plate will keep on changing. When the mobile plate changes, automatically the distance changes. So the capacitance will be, if the distance is less, epsilon A by D, the capacitance will be high. If the distance is high, more, then the capacitance will less. Capacitor value is less. So this is the, in this way we can find the capacitance value by changing the distance as well as by changing the area. So next one is the piezoelectric element. So piezoelectric element, we can also use the piezoelectric element like quartz. Quartz we can use. And so this is the one is the top electrode. You have two electrodes will be there. One is the top electrode, this is the bottom electrode. In between this, you have a piezoelectric element, quartz will be placed. And you have the connection for the top and the bottom. So when you apply some force, what will happen? It undergoes deformation. It undergoes deformation and it produces some positive and the negative ions will move. Here, due to the deformation, positive ions will move and negative ions will move. So this will produce some voltage. So that we call it as piezoelectric. effect. This we call as piezoelectric effect. So next comes the sensor, ultrasonic sensor. So it is a type of the electronic sensor that uses ultrasonic waves, using the ultrasonic waves to determine the distance between the two objects and converting the reflected sound into electrical signals. Okay. So here what will happen is you have to keep some ultrasonic sensor here. Okay, so this will be used for detecting the level. For example, this is the here you have the sensor. The level of the water is at the down position. Okay, as the level increases, the level will increase. So the level increase, what will happen? The ultrasonic sensor will send a signal. So the signal will fall into this and immediately come back. Sound waves will go and it will come back. That distance will be calculated, and the distance is given by time into speed of the sound by 2. The distance will be calculated. So the distance is calculated by measuring the ultrasonic sound travel, how much amount of traveling time per and the speed. Based on that, we can find the. So the sensor, ultrasonic sensor, to calculate only the distance. It will measure this. What is the distance? How it will measure the distances? It will sense the object direction and immediately it will come back. That distance it will measure, and how much amount of speed is taken to detect that thing, that we have to measure. So that is the use of this ultrasonic sensor. So that's all about the module 2. So in this module 2, just a recap of the module 2, there is classifications of sensor 1. First, we have seen the mechanical sensors. What is a mechanical sensor? And what is an electromechanical sensor? What is electro and mechanical? What is this combination? And then under these electromechanical sensors, we have different classifications like resistive. In resistive sensor, what are the different methods? Strain gauge and potentiometer have seen. And then coming to the next resistive sensor is change in the resistance. And inductive sensor, we have seen LVDT. Then we have different types. We have what is the mutual induction type, and then reluctance type. So, and then we have seen LVDT comes under the transformer reluctance type. Next comes the capacitive sensors. So there we have, and then we have seen proximity sensors, and finally we have seen the ultrasonic sensors. So I hope you have understood the concepts of the different types of sensors in mechanical and electromechanical. So let us meet in the next module. Thank you.